Welcome back for part 2. Okay, let's check your 8 questions. So you can see the first 3 answers here. All 3 of these are convergent. The first one approaches the value of 2. You can think of that like you would think about this function and how you have equal degree. So the leading coefficient tells you the end behavior, and behavior and limits are the same kind of thing. Because both are dealing with as you approach infinity. And then limit is 0 for the next one because the bottom is going to get bigger, 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 whereas the top has to stay between -1 and 1. For number 3, you should get the answer of 3 because the part that I circled there is approaching 0 as n goes to infinity. Question 4 was just my opportunity to remind you of the limit definition of E, which I have in blue there. And there really isn't a great way to know that other than to recognize it. You might have figured it out if you used a table and then just let n get larger and larger and larger. On your table, you will see that you're approaching 2.718 something. Number 5, that overall limit is pi because this portion has a limit of pi over 2, which you maybe would know because of what tangent does. Tangent has an asymptote at pi over 2 that is vertical, and so arctan has a horizontal asymptote at pi over 2. This is my picture here. And so there's an asymptote at pi over 2, and there's an asymptote at negative pi over 2. But as we approach infinity, it's this part that we care about, right? Because we're looking at that behavior toward the right. So if that part that I underlined in pink, the arctan, is approaching pi over 2, then overall multiplying that by 2 is going to approach pi. Number 6, diverges. That is something that's just getting larger and larger and larger for all time. Whereas number 7, although similar in structure, these both have a number as a base. They both have an n as an exponent. This second, number 7, actually does have a limit, and that limit is 0 because this is ever shrinking, whereas 6 is ever growing. And then number 8 is divergent. And you might recognize this as being an arithmetic sequence. If we plug in 1, and then we plug in 2, and then we plug in 3, you can see that we are just constantly going up by a half. And that's what we mean by an arithmetic sequence, is that there's a constant rate of change. But all arithmetic sequences are very, very boring in terms of convergence and divergence in that they all diverge. So we don't spend a lot of time on arithmetic sequences for that reason. All right, let's dive now into series. So be very cautious. Both of these words today start with the letter S, and you're learning them on the same day. And I sometimes think that that is what makes people confuse them. Sequences are what we were just talking about. Those are lists. But series are sums. That's when you add together things. So if I had a sequence, and instead of having commas, I wrote addition signs, I now have a series. Okay, so the first one's a sequence, the second one is a series. Now, I know we just learned about sequences, and they do matter some, but really what matters the most are series. Okay, series are where we're going to be spending the vast majority of our time because it turns out that adding together a lot of things is super important in the work that's coming ahead in calculus. Okay, an infinite series, well, we just said series is when you add stuff up. And infinite means you have infinitely many of them. So it's a sum with infinitely many terms. So it's like an addition problem that goes on forever. And so my question to you is, can an infinite number of terms add up to a finite value? And it turns out that the very interesting answer is yes, that sometimes can be true. So that's what we're going to be investigating. All right, in order to investigate that, something I want to explain to you is the idea of a partial sum. So if we have this idea of having an infinite number of terms, okay, so I am just labeling these a sub 1, a sub 2, a sub 3, meaning first term, second term, third term, fourth term, fifth term, okay? And this goes on forever, hence the ... What I mean by a partial sum is just adding together the parts of this infinite sum. So S sub 1, the first partial sum would just be the first term, whereas the second partial sum would be the first two terms added together, whereas the third partial sum would be the first, oops, I just wrote the wrong thing, would be the first three terms added together, and so on. Okay, so now the definition of sequence convergence was just think of sequences like limits. The definition of series convergence is different from that, but it turns into a sequence statement, if that makes any sense, okay? So this is a definition, and it's an interesting definition, but it actually comes with a warning, which is down here, okay? So let's take our time on this. So think about an infinite series, such as this thing in purple, okay? So we have this infinite series. If the sequence of partial sums has a limit, converges to some value s, then the series itself converges, and s is the sum of the series. So let's go back to this very confusing part of this statement. The sequence of partial sums. The sequence of partial sums would be this: s sub 1, comma, s sub 2, comma, s sub 3, comma, and so on, where this bit, for example, is adding the first two together. This is adding the first three together, okay, and so on, okay? So if you find the partial sums, you make those partial sums into a sequence, and then look at that sequence and determine if it has a limit or not. If that sequence of partial sums has a limit, then the series, meaning this thing in purple, then the series converges. If not, then the series diverges. Now that's the actual definition of what it means for a series to converge. However, that definition isn't the thing that we use as a test. Okay, so like to check if something is true, that's the test. There are going to be a whole bunch of different tests, and I do mean a whole bunch, like 10, okay? There are going to be like 10 different tests that we use to determine if a series converges or not. None of those tests is to write out the sequence of partial sums and see if that sequence converges, okay? We don't actually do that. We do other things as proxies to see if the series has that behavior. So the first such test is the one we're learning today, and this test only applies to series that are what we call geometric. So a geometric series, first of all, series means that you're adding things together, and the term geometric means that you have a constant ratio or a constant multiplier. So from one term to the next, you are multiplying by the same thing. Okay, so in this particular problem, I'm looking at this series, 3/10, 300ths, 3,000ths, 3/10,000ths, etc. Now, if you think of this as decimals, I think that especially can help you to see how we automatically know that this is going to be a convergent series, right? If you just think of adding these decimals together, right? This is the decimal for that fraction, this is a decimal for that fraction. If you think of adding those together, I think you see that you get 3's all the way down, which is a third, okay? So this is a series, an infinitely long addition problem that has a finite sum. Pretty weird, right? I think that's weird, okay? So the reason that we can think of this as geometric is because if we look from one term to the next, like let's say from 3/10 to 300ths, or from 0.3 to 0.03 if you prefer, we're multiplying by something, going from one term to the next, and that thing is 1/10. Right? That's why the decimal point moves one place. That's why you get another 0 in the denominator in fraction form. Okay? So that R value in this case is 1/10. If I didn't know that, I could take any particular number in the series and divide it by the term that came ahead of it, right? That's how you figure out how you're multiplying, right? Whatever I'm multiplying by, going left to right, I can divide going right to left and see what that number was. Okay? That number is what we call the constant ratio. Now, there's going to be a big ta-da that happens down here, okay, about that constant ratio. And what I'm going to show you in the next little bit is the derivation of that big ta-da, okay? So let's go through and see what we think of that. So let's think of our generic infinite geometric series as having this form. We have a first term, a sub 1, and then going from one term to the next, we multiply by r, and then we multiply by r again, and then we multiply by r again. That's how it's generated, okay? So think of that having just a finite number of terms. Cut it off at some point at n terms, and we're going to call that the nth partial sum, okay? And then if we were to take that equation that I'm putting a blue star by, if we were taking that equation and multiplying each term by r and then lining them up with the row above it, a sub 1 times r would give me a sub 1 times r, and I am matching that up with this. Then if I take the next term, a sub 1 times r, and multiply it by another r, I'm going to get this, and I'm lining that up with that, okay? So hopefully you see that pattern. I am just multiplying each term in the previous row by another r, which means that this term would be a sub 1 r to the n minus 1, and I'd have an a sub 1 times r to the n. And then on this side, I'd have s sub n times r, okay? Because I multiplied the entire equation with the blue star. I multiplied every single term by an r, okay? Now, if we were to subtract those, okay, I want to take this part here and subtract this. No, the other way. Sorry, my bad. I already had it written the other way. I was going to do it a different way, but it's on your page this way. Okay, so here we are. So if I take s sub n and subtract s sub n times r, okay, which is what this is, r times s sub n, whatever, okay? So take the blue star line and subtract the pink star line, okay? If I were to do that, I would end up with most things canceling out, right? Because this would cancel this, this would cancel this, this would cancel this, this would cancel this, this would cancel this. But the things I'd still have are these two pieces right here. So I'd have a sub 1 minus a sub 1 times r to the n, okay? So if we were to factor now, factor out the s sub n on the, oh, I keep bumping things. Factor out the s sub n on that left-hand side, and on the right-hand side, factor out a sub 1. And then reorganize it, it gives me this formula, which you may have seen in an earlier math class. I'm not positive if they still cover this or not. But that is a formula for finding the first n terms in a geometric series. Okay, so like if I wanted to figure out what the first 10 terms in a geometric series added up to, then n would be 10, r would be my ratio, a sub 1 would be my first term, okay? So we don't actually want to think about having n terms, though. We want to think about having an infinite number of terms. So I want you to think about what happens in these three cases. So first case, what happens to this formula if r is equal to 1? So if we were finding the limit of this as n goes to infinity, here's my first term, r is 1. Well, that is kind of crazy, right? Because we get a 0 over 0 situation. Furthermore, what would our series look like? I'm just multiplying by 1. I'd get the same thing the whole time. This actually goes to infinity. It's divergent, right? Very boring case. Whole series of the same thing. The divergent is easier to see if you think about this, right? If you just have 5 plus 5 plus 5 plus 5 plus 5, that's divergent, right? It's not approaching anything. It's just getting bigger and bigger and bigger over time. All right, now let's think about what if r is a number between -1 and 1. So pick your favorite number, 1/3 or something like that. This is going to shrink big time, approach 0. And so this limit, 1 minus something approaching 0 is just 1. So on the top, I just have a sub 1. On the bottom, I'd have 1 minus r. So it turns out that if I'm in this case, if, then my series converges to that value. If I have a number that's bigger than 1 as my ratio, like let's say 2, okay, I'd have a sub 1, and then I multiply it by 2, and I multiply by 2 again, and I multiply by 2 again, something like that. I think you can convince yourself too that that also diverges, okay, because it's just going to get bigger, bigger, bigger all the time. So that's our big thing, okay? Our sum of an infinite geometric is found by a sub 1 over 1 minus r if and only if our ratio is between -1 and 1. Okay? Otherwise, we will have something that diverges. Okay, and this is only for geometric series. And that's the first of about 10 cases or 10 tests that you're going to learn for series convergence. Thank you for hanging in there. I know that was a long video. Much appreciated.